Hello. Hope you guys can hear me. Welcome back and Happy New Year to everyone. It has been a couple of minutes. It's been a couple of weeks actually, but we're back. We're going to be doing some more WebAssembly today. Not directly related to the operating system, but this will definitely be big in helping us with that operating system. So we're actually going to be looking at how to implement actual how to write raw WebAssembly text. So we've looked at the website WASM 2want a lot before to analyze kind of what our WebAssembly code is actually compiled down into, but we haven't written that ourselves, and there are tools that can help us do that, and we're going to be looking at them today. So a couple of prerequisites. Let me point out, I don't know where my desktop is. Here, hold on. This might be a little more volume friendly. Okay. Alrighty. Okay, this is good. So I put a guide in the README file, which will actually instruct you on how to download some of these tools. So the first one is going to be the WASM tool suite. It's a Git repository that you need to clone, download all the files, and then you also need to get CMake in order to build the files. And then once you have that, you can go and do things like WASM 2want help. So for example, if we wanted to look at one of our examples, so we have WebAssembly tutorial. We have, where am I looking? CD exported function. And if we wanted to say WASM 2want exported.wasm, you would get the entire WebAssembly text format of the WASM files that we've compiled from our C files. But we don't really care about this. We want to write it ourselves now. We want to get into the nitty-gritty, because look at how much code is here just for a little bit of this was, I think, the exported functions, and look at how little C code we wrote. But the reason why it's so long is because we have libraries like standard lib, and we take malloc and current time is exported, but srandom, seed random. So stuff like that is where a lot of that code comes from. But even if we didn't have all this, there would still be a lot, because we still have mscript and .h here. But we're going to write our own WASM code so it looks like this, and that's all we're going to do. I want to install the WebAssembly toolkit, because this is going to be very helpful with IntelliSense. So we will look at that. Alrighty, let's get going. So I have my folder, raw WASM, and we will start with a simple example. So we'll first create just a WAT file. So it's going to have the extension WAT. So we'll call it add.wat. And all WASM files are built on a module. So the module is the outermost element, and this syntax you'll see is called S expressions, because they kind of look like an S when you put the parentheses like that. So that's kind of where the S expressions come from. So you have the module as the outermost element, and that's going to be what we have. So we can actually compile this right now. So if I were to go to raw WASM, and I wanted to say WAT to WASM, add.wat, we'd be okay. So I'm taking the tool. This is essentially our assembly compiler here, WAT to WASM. And then we pass in the file, and then if I list my directory, we see that we have the add.wat, which we already had, and then add.wasm. And when we do the reverse, so WASM to WAT, add.wasm, we should get the same thing, and it's just an empty module, just like this, with fewer characters, of course, but you get the gist. So that's what we are working with so far. let's create a simple function. So again, all WebAssembly elements will be held in these curly braces or in these parentheses as expressions. So we're gonna have a function. So that's all it's called, func. And then we're gonna give it a name. So you start the name with a $sign. So we'll call it add, and we will have two parameters. So we'll have param i32 and param i32. So these, which you can see, I'll zoom in here actually for you. So you can see that we have add, the function name here, and then the parentheses will also contain our parameters, or just our data. So we have our parameter, and it's of type i32 or integer 32. Now we also want to give these a name. We'll give them a name in a second. But so we have our two parameters here, and then we also have results, which is just the return, and it has a type as well, i32. So now we can start writing code. So I'll go into WebAssembly for now, or into OneNote, sorry. Just to kind of explain how writing code will work. So if we have our existing, so we have our parameters, these are going to be in our local store is what it's called. So we have 0, which is the first parameter. 1 is the second parameter. So these are local variables, and we can modify these using local.set, and we can give it an index. Oops. So if we were to say local.set 0, that would set the 0th local variable. But question is, all right, so you may or may not have seen assembly code before. I'm going to assume no. But a lot of assembly is simply like calling a function. You have, at least for ARM v8 assembly, you have an instruction like add, and you specify some register values. So you specify an output, and then you do R1 and R2, and this is equivalent to R out is equal to R1 plus R2, where these are register values, or just local variables on the CPU that are stored on the CPU currently. But there's none of that. We're not going to see any of that in WebAssembly. Instead, WebAssembly operates with a variable, a data stack. And if you've watched the videos that we had on the shunting yard algorithm and reverse Polish notation, this is really going to grind your gears. It's exactly the same thing. So essentially, we're going to keep putting data on the stack, and then we're going to pop it using functions. So for example, I can create a constant. So something like i32.const 1. And then my stack now looks like this, 1. And I can also have i32.const 3. And now my stack looks like 1, 3. And I can keep anything that will output a number. So a function call like add will return to the stack. We'll put something on the stack. But these function calls like add, or any external functions, something that takes a parameter like this, param i32 and param i32, these will essentially take from the stack. So if I call a function like i32.add, this is going to take no arguments, because it's just going to take 1 plus 3, and then it will add it, and 4 will be on the stack. So essentially, the add will pop 1 and 3. It will pop 3, then pop 1 from the stack. So these two are popped. Then it adds them to get 4. And then the stack now contains the result of that. And then we can use this value in another operation. So if we get another constant, i32.const 6, we now have 4 and 6 on the stack. And then we can pop it with a function call. And if we wanted to call our function here, add, we could do the same thing. So this calling a function is relatively easy. It's like using assembly, where you call and then you give the label name, which is add. And then what will happen here is it will take 4 and 6, pop them from the stack, and then it will compute the result, 10, and then it will put 10 on the stack. Now, when returning from a function, you need to have this return type on here. So we're essentially going to, so this is just an example here. So I will scroll down. So we have currently our locals. So we have local. So we have 0, which is the left-hand side. I haven't given it a name yet, and then the right-hand side. So we'll just leave it like LHS and RHS for the moment. So let's just assume that. Now, in order to add these, we need to get them on the stack. So they're currently stored in a local variable, but we need to put them on the stack. So what we're going to do is we're going to say local.get 0, and that index is 0. Then we're going to say local.get 1. So now our stack, after these two instructions, after the first one, it looks like LHS, so the left-hand side, and then we have RHS. Sorry. Then after getting the second one, we have LHS and RHS on the stack. So two variables on the stack. Then we're going to call the instruction i32.add, no arguments, and it's just going to take the top two values in the stack, and then we'll compute the sum. And then when we return from the function, there's no explicit return statement, but once we hit the end parenthesis, sum gets returned. So the stack is now empty. So we're going to be operating under stacks all day long, which will be very fun. But you'll get used to it. And again, if you've done reverse Polish notation, this may be a little familiar to you, but we're going to assume that you have it for now. A reverse Polish notation won't directly help you, but it's kind of the same. It's the same principles where you create a stack of data, and then as soon as you hit an operator or a function, you pop from the data stack and use the pop values as arguments. So let's do this. So local.get 0. That's going to get the 0th local variable. Then we have local.get 1. So we have put LHS on the stack, put right-hand side on the stack, and then i32.add. Pop from stack and compute. So this is the entire function right here. This is the function. So i32.add, once again, will take the top two variables on the stack, top two data values on the stack, and it will compute the result, and then it will put that value on the stack. And then we return right here. And it just returns whatever's on the stack. And I'll show you compilation errors from what happens if we deviate from this. We're not done just yet. We won't be able to call this function from JavaScript or from an HTML file or whatnot. So we need to actually make this. We need to export this function. And good for WebAssembly, it's relatively easy. You can call export add. And this is the name of the function that will be called in JavaScript, and then we just give it the function name. So func add, the exact signature that we have right here. Just like so. So let's go ahead and compile. We'll do the same thing. So we have wat to WASM. Here I can actually do this in Visual Studio Code just so we can see everything a little better. Oh, you know, this is crowded. We're gonna do it right here. So I'm gonna give it the function or the file name and no compilation errors. And then if I go ahead and do the WASM to wat, we get the same thing. So we have, let's look at what we have actually right now. So we have the reverse or the disassembled version has a couple of extra lines here. So there's a type, the function, and it doesn't name the parameters or it doesn't give the parameters separately. It just has them as their types, and then we still have the same result as you can see here. So this is the result that we have. Then this is the actual function declaration here. So function 0. So we first declare the type of the function, or WebAssembly wants to do that. So we have our function, the type 0, and then we have our instructions that we already wrote, and then the export call, which is the exact same, except this time you just call an index of a function this. But it still has the same name. Okay, let's write our HTML file so that we can actually call this. So I'm going to call this raw.html, and we'll have doc type HTML, head, title, raw what, and body. All right, and then we'll have our script here. So we're just going to be creating a bunch of little modules here. So I'm just going to create one general function called run module with a name. And we're just going to set up the streaming. So because we have a WASM file here, the process becomes the exact same that we have already seen. So we first set up our memory block. So variable memory is equal to new WebAssembly.memory, initial 256 pages, maximum 512 pages. And then variable exports as per usual. Then we're going to have our WebAssembly.instantiate streaming. And we're going to have the fetch here. So fetch, and then we'll just call it by name. So this will be $. We're going to do some string interpolation in JavaScript. .wasm. And then let me just look at this. So we have our instantiate streaming, get the WASM file that we have compiled, and then we're going to give it our object. So we're just going to start with JS and the memory value. So mem is memory, like so. And then after we have streamed the file, we're going to call a function. So then results, we say exports is equal to results.instance.exports, and then memory is equal to exports.memory. Right? Yes. All right, and then we're going to have just a result value that we'll write to, and otherwise we are going. And then after that, we're going to call our modules. So if name is equal to add, then we're going to try and perform an addition. So result is equal to exports.add, and we'll give it 15 and 16, like so. And then afterwards, we'll console.log the name and the results, like so. All right. So once again, we have run module, which is just a JavaScript function. We're going to set up streaming as per normal, as per usual. And then we're going to call our module here. Let's just create a button or two to do this. So we'll have a button on click is equal to run module, and we'll give it add here. All right. Add. All right, so let's start our HTTP server. So let me go here, cd source/wasm. All right, so we have WebAssembly tutorial raw.html. Let me go to my console, zoom in, click add. Run module is not defined. That's here. because I misnamed it. Beautiful. 15 plus 16 add gets you 31. So the exports and the functions, they all work the same. There's nothing different about that at all. It's just we're writing the code ourselves instead of taking C and using emcc to compile it. We can use both at the same time. There's no problem with that. We'll actually look at some point on how to combine the two using emcc, but this just seems much easier instead of writing an int main and defining a function there, including a header, and so on and so forth, generating that long WASM file. So this is the introduction here. Let's do one more thing. With this, let's give our variables names. To make variables a little more recognizable, instead of using indices, we can just give them names and refer to them using those names. Makes it super easy. Like so. And if I compile again, here, like so. And if I do the other side, again, the compiler will generate code that doesn't rely on the variable names because it doesn't need those. So this will always default to the indices. But if we do the same, we get add 31. Excuse me. All right, so that's add. Pretty simple. Let's look at a couple more examples. There's also, I should mention this, but there's a repository. There's a link to it in the README that has plenty of examples here on how to use WebAssembly Text. And I'm taking a couple of examples from here, but I'm also doing some of the stuff that we haven't looked at before. I'm replicating some of the examples that we have done before, adding on to them. And we'll look at that here, actually. So go back here. Let's create a new WAT file called func.wat because we're going to have multiple functions in this one. So start, same thing, module, like so. This time we're going to have multiple functions in WebAssembly, but we're also going to have functions that are taken from JavaScript, so in that import object. So we'll start with just the local functions. So again, define your function using the parentheses. We'll just say get val results, and this doesn't take in any parameters, it just has a result, so i32, and it just returns i32.const 42. So if I were to, I'm going to compile this right now for you guys. Func, like so, and then wasm to wat, func.wasm. It gives the exact same thing. There's nothing new here. So sorry about that. Oh, man. I don't know why that happened. That was just, I think the power cord for my computer, I need to manage my wires a little better. We're back though. Nope. Here we go. Okay. Just make sure I have everything up. Okay. We're back online. So sorry about that. I don't know why that's happened before, unfortunately. Not the first time. I should know better. Okay, we're back. Okay, so we were just at here. The simple function has so this function here is as simple as it gets. It just puts a constant on the stack and then just returns it. Now let's try and break this function. So let's do something like i32.const 50. Let's just see what'll happen here. So if I go want to WASM func.wat, it will give me an error because there's a type mismatch. Because at the end of the function, it had two values on the stack. It had the first constant and then also the second constant. Now let's make this simple. Okay, i32.add. This should fix it. Yes, it does. Let's do something with this value. Let's have another function here that just takes in a value but doesn't return anything. So some func parameter i32, and that just does nothing. So we can call this function using call sumfunc. And if we do this, there might be a couple things that break, but I know one should definitely break. Exactly, type mismatch in implicit return. Expected an integer but got nothing. So we put 42 on the stack. So our stack here was 42. Then it was 42 and 50. Then our stack after adding was 92. But then call sumfunc took 92 off the stack, so our stack was empty, and we are expecting to return something here. Hence our error. So we need to on this. There must be exactly a certain number of values on the stack to return. So I've actually haven't tried this yet, but let's try having two integers on the stack up here and see if this works. Oh, it does. So I guess we can return multiple values from a function, and I'm actually interested to see how this will work. So let's go to raw.html. Else if name is equal to function, I want to call the function getVal. So a b is equal to exports.getVal, like so. Does this not work? JavaScript doesn't like this at all. Const declarations. I don't know how to do. Is it like this? Let's just say result is equal to that, and we'll see what it returns. So we are here. We have our web server up. Let me go here. I didn't create I did not create my button. Like so. All right, open up the console. Func. Exports.getVal is not a function. Yes, because I did not export it. Need to do the export here. I believe you can do this inline, actually. Let me check on that. Yes, you can. Okay, so this function, you can actually just call func and then in parentheses exports getVal, like so, and this will export the function to JavaScript. And I believe the syntax is correct, even so we can still have the name to call it locally, but it exports it to JavaScript nevertheless. You can give an explicit return. If you want to break, there's a conditional way to break. We'll look at conditionals actually in a second with break conditions, but it's implicitly returned when you hit the end parentheses of the function. Okay, so unexpected token. Okay, so we cannot have the local name unless that's over here. trying a bunch of things. It does work. So in order to have a function that we can call locally, we need to have func getVal, but then we export it using the name export getVal. So let's try and run this again. Okay. So WebAssembly will actually return 2 values to you in an array, which is super cool. But you can also see how the order it returned it. So the top of the stack is at the end of the array. So the top of the stack is at the end of the array, and the bottom of the stack is at the beginning of the array. So it's just, the only constraint is that it must match the return type here, I32 and I32. Okay, so this is a little function here. And I guess we never really called SumFunc, but let's just call SumFunc here. And I want SumFunc to return an I32. So I want SumFunc to say add 20 to our parameter, to our param I32. So we'll say local.get0 and then I32.const 20 I32.add. So we put this on the stack, the local parameter, then we put the constant 20 on the stack, and then we add them. And now what we should have in call SumFunc is our parameter, the initial constant 42, and then 50 plus 20. I believe that ordering is correct. So 42, then 70. That should be our stack, and that's what we should return. So let's compile func, and then we have 42 and 70 as expected. Good stuff. So this is how we call functions locally, like this. Now let's have an imported function, so like a console log. So we have import console. So we're gonna have several names. We're gonna have 2 names for it. So the module, so we'll call it console, and then the function name is log. So console.log. This isn't referring to doesn't implicitly refer to console.log, but we're gonna make it refer to it. But this is the module, then the function name. So, and we need to define its type. So func log, and then we give it a parameter I32, and this is it. So we have our type here, the signature. Local.get1. So if for this one, for example, local.get1 would be out of index, I believe, unless it wanted to give us the result. Because I'll show you to the WAT here. So when we initially wrote this, we had this as local.get0 and local.get1. So these are referring to the indices of the local variables up here. So we have 0, 1, then the results, which I'm not sure if it's directly. Let me see. I don't know if this is included in the index, but it's 0, then 1, and then we will also have other local variables if we decide to declare them. But local.get0 and 1 are just indices of those variables, but we can also use the names like this. Okay, so we have our imported console log, takes in a parameter I32, and this will just be a number. So we want to log some number. So we'll have func compute export compute. So this is the exported name, and it will return an I32. So let's have a constant I32.const 13, and then let's call our log function here with this number. So call log, like so. And then let's get our two numbers function here. So we currently have nothing on the stack because log does not return anything, so we should have nothing on the stack. So we'll do 13, nothing on the stack. Then I want to get two values on the stack, so call, and this is called getVal. So we should have 42 and 70 because these are implicitly returned here. So 42 and 70. And then we will have i32.add, and this should return 113. So compute should return 113, but also log the value 13. Or this should be 112, sorry. All right. So let's compile this. Good. Let's actually take a look at the WASM 2 watt just to see what it looks like. Okay. So we have our parameter i32, which is the console log type, and that type is referred to here. So we don't need to explicitly say the parameters every time. We can just give it the type. So then we have our type. This is for, I forget which one this is for. That is for some func. That type is here. Then the second type just returns the array, so the 42 and 50. And then the third one is our compute function that we're exporting. So we export compute, which is func3, this one, and then we export getVal, which is number 2 here. And then also notice how when we import, we just give it the type, the signature type, but the names stay the same. All right, so now in our JavaScript file, I don't want to call getVal, I want to call compute. And compute does not take any arguments. So let's go ahead, func. Okay, console is not an object, right. So now that we have an imported function, we need to give it that value. So we go into our import object here. We currently have memory, so that's under the JS module, but we're going to go and create another module, console, and log will just point to console.log. So I'll just make this log num so there's a distinction here. Log num, like so. All right. Func. Console is not an object. Did I not? Oh, I need to reload. That's why. There we go. Okay. So a couple of things here. Note that the value 13, I don't know if you guys can see that. I'll go in as far as I can. Number 13 is printed from the WASM file here because this is what we call. So we call console.log from the WASM file. That's the imported function, or that's the function that JavaScript exports and WebAssembly imports. Then func112, func is the name, and 112 is the result. So we are printing this from our JavaScript file. This is getting printed right here. All right. So that's all I want to do for functions at the moment. Let's take a bit of a detour and go into some exported memory. So I'm going to create another watt file, mem.watt. And we will have our empty module. Again, you can compile this if you wanted. And we will this time, instead of logging numbers, we want to log some strings that we're going to store in memory. So we'll start by saying import console log string. So the console module log string is the function name. And we're going to say func log string. And this takes in a parameter i32 and I32. Or should we just give it one parameter for an address? All right, so we want this here. So this is our import function. We essentially want to call this. And the I32 will be the address of the string. So we're going to call it, say, function print, and we'll export it with the name print. And this will return I32. And let's say we have give me 2 seconds. I'm just trying to parse through my example because it kind of makes no sense. Okay, so we want to return a result here, and this will just be a status code per se. So say I32.const 0, and this would be completely legitimate. So if I were to call this like that, we'd be okay. Now I want to store a string. I want to put a string in memory, although it's not that easy because, well, how do we return a string? We can only return numbers, really. So what we need to do is we need to give memory. We need to provide our exported memory, or meddle with the memory object that we have. So what we will say is we're going to give our memory module, or not a memory module, a memory element. So it's going to be called memory, and we're going to give it a name, exported memory, and it's going to be initial 10 pages and expand to 100 on maximum. This looks syntactically correct. So that is that. Then we're going to export this memory. So we're saying, when we say export, the name is the exact same, so memory. And then we just say memory, exported memory, like so. So this memory, exported memory here, that refers to this line up here. And then the name is just what we take in exports. So exports.memory, WebAssembly has been implicitly compiling to this export statement here. Now to actually set some values in this memory, we need to define a data element. So data, and we're going to give it an initial address of 0. Or sorry, 0, I'm not entirely sure what this parameter is. Haven't found much documentation, but the address is then given here, I32.const 0. So this means that we are starting at address 0. And we're defining some memory. And you can do that using strings, or what look like strings, but are actually compiled to integers. So this is the address. And then we're going to have a bunch of strings that you can either write, or I know you can write in hex, and I'm going to try and write it in an actual string format. So A, W, what's it? WASD. So that's 4 bytes. Then you go on to the next one. Let's go 2, 3, 4, 5. Now these are characters. These are Unicode characters, or UTF-8 characters. And then I want to terminate the string with the \00. This backslash means hex. And then we'll just have a couple other zeros, like so. So what I want to do now is, in print, I want to call our log string passing in this element. And or in log string, I want to take in 2 values. So I want to take in an offset and a length. So in order to call this function, we need to put our parameters on the stack. So I32.const 0, this is the offset. I32.const, and the length is going to be 1, 2, 3, 4, 5, 6, 7, 8, 8 characters. And then I want to call log string. like so. So call log string, which calls this imported function here. Okay, let me zoom out so you can see the whole thing. But so that we are statically putting the message in memory. We're going to dynamically change that, but for now we're going to start by statically doing it. So let's program our new module. Mem and mem, and then else if name is equal to mem, result is equal to exports dot, and we are exporting print. And note again how exports.memory corresponds to this. So let's check the compilation to make sure that we can store characters like this. I just want to confirm that. Good. Let's take a look at the WASM 2 WAT. Like so. All right. Okay, so we have our function types as per usual. The import here. This is going to be the print function right here. And then here we define our memory. So memory index 0. And we export memory like that. So this is just memory 0. And then we have our data, which you can see this is type 0. i32.const 0. So what I'm thinking now, what I'm starting to think is, there isn't much documentation on WebAssembly Text, but this 0 corresponds to this 0. So if we were to have multiple memories in here, we could have memory, say 1, and then data 1 would be setting the memory on memory 1. So let's try that actually. So we'll say memory, private memory, and then we'll give it the same a little bit of different data. Like so. Only one memory block allowed. Okay, so you can only have one memory block, and that makes sense. And you can only have, again, I'm not sure what this 0 parameter is, but this is the address that we're setting it for. If we wanted to say data 0 and then set some values later, i32.const, let's say 48. So this is our address, our new address. And we just wanted to set a couple of characters, WASD and then \00. Then we could also call log string again with these new parameters. So i32.const 48, and that would be 48 bytes. Offset i32.const 3 as the length. Call log string. So we have the same memory, but we are now setting static data in 2 different spots. Let's see if this works, and it does work. Okay, perfect. So now in raw.html, we have exports.print, but now we have another imported function that we need to deal with, console log string, which takes in 2 values. So log string takes in a cursor length. I actually want to define this functionality here just so it's a little cleaner. Function log string takes in a cursor and a length, and this will operate on WebAssembly.memory. So this actually, since we're not importing any memory, we don't care about this right now. If we want to import memory, that's a different story, but we're always exporting our memory. So memory is always getting exported, like as it says here. So log string, I want to just point to log string. And then in this function, I want to take the buffer. So we need a variable buffer is equal to new uint8 array of memory.buffer. at the cursor and length. And then what we can say is console.log, and okay, this is where I get screwed up on how JavaScript works. logger2.html, new text decoder. Beautiful. Okay, so it's going to be, we're going to console.log new text decoder utf8 dot decode buffer, and that's it, right? That's what it says here. Okay, so let's try it. So again, we are creating a new imported or new function to export to WebAssembly, where WebAssembly calls console log string twice, 2 different spots in memory. So we'll recompile. Now we have memory, and please work. Aha! It does work. Beautiful. So we have WASD2345, which is the first string, and then ASD, which is the second string, and we are pointing to them in 2 different spots. So the 2 different pieces of data are right here. Let's try changing one of the characters, actually. I forget. Let's try and do something funny here. Let's say i32.const 48. So I want to set some memory dynamically. So this is our offset, and we're putting it on the stack. Then I want to set a value, i32.const, and then I'm going to give it a string, ASDF value, and then I want to set the value in memory, so i32.store. So this is another function here, i32.store. We can also call i32.store 8, which only stores a byte, but we're going to store the whole integer. You can also call i32.load, which is cool. So something like i32.load. We will actually do that. So i32.store, and then I want to then set the next integer as a terminator. So i32.const 52 offset, i32.const 0, i32.store. And store, I don't believe, returns any values. So this is our terminator. And now I want to call log string again, although this time with the length of 4. So let's want to WASM. Okay. Okay, so it seems that we cannot do this as an integer literal. Okay. Is there a way to do this? I expected a numeric literal. I'm forgetting. Alright, so let's... I know this will work, though. Let's try setting a character. So i32.const 51 is our offset. i32.const some utf8 char code, and then i32.store 8. So we're only going to store 8 bytes or 8 bits. Now I want to get utf8. Okay? Let's open this up. Python ord of f. Does that work? 102. Beautiful. So the constant value is 102 that we're looking for. So we're going to put the value 102 in memory at location 51. So let's try that. Okay, it works somehow. Let's reload. Oh my god, it works. So our first string is ASD, and then we tack on the second character. And it's just like that. It works. Cool. Amazing. Let's get a little fancy here. Let's say log string length, because we explicitly pass in a length. But what if I don't want to do that? I want to just be able to set a terminator. So log string. So that would just be, that would look like length, and then no length this time, but I believe we can still, this buffer will still work because it's going to look for that terminator character automatically. Although I'm not 100% certain. Don't quote me on it until it works, in which case I'll take all the credit for it. This is log string. And now here I don't want to call, whenever we call, I'll call log string length the first time again, but the second time I won't. So whenever we're calling log string, we don't have the second length parameter. So we only need one integer on the stack. So this needs, we need to get another imported function, log string, and it only takes one i32 parameter. Let's compile. Cool. Okay, so we do need, okay, so we do need to explicitly find a length here. So don't quote me on the fact that this works, all right? Decode, is there a way? Okay. We're going to look for terminator. So let I is equal to 0. I don't even know what to say for I is less than. Can I say buff.forEach and then C plus I is the increment, and then if C is equal to 0, can I break out of this? I know I can't do that because it's not a loop. It's a function that gets called. For each. No, okay. I have no clue what I'm doing. Let I equal 0 while I is less than buff.length. That should work, I think. If buff at I is equal to 0, break. Otherwise, plus I. And then now I want to say buff is equal to buff.what is the what's the function that slices them? There has to be a function for this. I'm almost certain there is. This is so embarrassing that I'm not prepared. Subarray, that's what I'm looking for. Subarray 0 and end at I, and I believe that is non-inclusive, so we need to plus I no matter what. All right. So this is our increment, and we just do it all in one step. Okay. Now let's check this again. Reload mem, and it works, but we should be not incrementing I every time. There we go. Okay. So WASD 2345. This is printed with an explicit length of 8 characters. Otherwise, we're looking for a terminator character, and we set ASD, and then we dynamically change it to ASDF. Let's do some, okay, that's memory. Let's look at a bit of control flow now. Why don't we? All right. That's memory. And now I want to go to this. So we're going to, instead of memory, we're going to do some flow.wat. And here we will do a bunch of, there's going to be a bunch of stuff that we'll look at here. I haven't done anything explicitly with if else, but we are looking at loops at the moment. So else if names flow okay, so this is just our new module. Again, start it, module like so. Make sure everything is working. Oops. Oops. Good. And then this should have our new function here, flow undefined. All right. So we're going to look at some control flow, and we're going to revisit an example that we looked at a while back. I forget if it was malloc or malloc. It was memory.c, where we accumulated an array. So we went through an array and we just summed all the elements. We're going to do that exact same thing, except this time we don't need a header file. We don't need any of that other shit. If you want to look at memory.wasm, like for example, cd memory wasm to wat memory.wasm. There is so much here. I don't even know what to say. There's so much here. I mean, it's not that much, but it's a lot. I guess there is the other thing of there's the string, but that's only this little part here. That should be nothing. That should be nothing because get string is function type 3. There's 19 defined functions in this stupid thing. Function 3 returns as literal an integer 1024. Also, to answer your question before, or the thing about the return values, yes, it seems here that local.set0 does account for result i32. So the result is considered a local variable, and it's indexed after the parameters, but before any local values. So let me just take this, just so we can take a look at it. So we have the parameters, two parameters here. i32, so 0, 1, and then i32 is index 2. So when we say local.set2, we're putting some value in here, and then we are also just getting it to put it on the stack. And then this is the explicit return call here. Okay. Okie dokes. Enough of that. Let's get into some stuff. So let's get back our integer log function. So we have a log num. So we're going to import console log num. This just takes in an integer param i32. So we're importing console module log num function name, and it just takes in a parameter i32. And we're going to have our accumulate function. So we first need to define some memory. So memory mem1. This just says, all right, we start with one page and we can go beyond that if we need. And then we want to export it with the name memory. Export memory. That's the string name, and then we need to reference the actual memory module here. So we notice how here, instead of defining explicit data, we're going to allow JavaScript to take control of that, and then we're going to tell JavaScript, hey, we want you to input the numbers into the array, and we're going to take care of it and compute the results. So we're now going to have our function. So function accumulate, export accumulate. So we are now visible to JavaScript. And we're going to take in a parameter, and I'm going to give the parameters names this time so it's a little easier to look at. So address I32, and then we'll give a number, so parameter n I32, and then the result is an I32. So this is the sum of elements, and we can actually put some comments in here to make this a little nice. Oops. So this is the size of the array, and then we have this n is the size, and then address is here, and then sum of elements. So we're also going to need to store a local variable, or I guess, you know what, since we don't even need a local variable at this point, we can do everything with right here that we need. Right here in the stack, we don't need another local variable. So again, this will be 0. This will be 1. So 0, 1, and 2. So let's start by initializing our sum. So i32.const 0 local.set2. So we set our sum to this. So let's just confirm that this works by setting it to some random value like 156. And then if I go to raw.html, I'm going to call accumulate, exports.accumulate. Let's make sure our wat compiles. WASM, wat2 WASM. Oops. Hold on. I want to do flow. There's a couple errors here. Unexpected character. What is up? Did I not save? Is this going to work? Unexpected token, ASM. These are all in line 1. Oh, because I'm trying to compile WASM instead of WAT. There we go, okay. Local variable out of range, max 2, type mismatch and implicit return, expected I32, but got that. Okay, so then to do our explicit return, we need to do local.getTo and return. This should have a couple of things, but we're still getting our out of range here. Local variable out of range max 2. I have 2. That's correct. What did we look at? Function number 3. Parameter I32. Oh, okay. So I was wrong. Result is not included in that count. You have to use a local variable. So this local variable is, let me just copy this, or I can actually demonstrate it to you here. So this result, it is not computed in local variables. We need to instead say local sum I32, and then this will be index number 2, sum to store. So what we will do, in fact, is we have our local variable, we get a constant, put it on the stack, and then we set the local variable, which pops 156 off the stack. So the stack is empty, and then we get that value, which returns it to the stack. So now, do this, works, and we should get 156, flow 156. Okay. That's kind of stupid, but I'm not going to complain. But point is, this is not included in local variables. All right, so we have that, and there. So that's sum and the initial value. So with control flow, WebAssembly works with things called blocks. So you can, there's a control flow stack, essentially nested levels, number of levels that you are in. These are defined by blocks. Blocks just define labels. And you can jump to and from labels, essentially. So, for example, if we wanted to start our block, it's just going to be using the same S syntax, so it has an open and close parenthesis, like so. And then we're going to define the block as a loop using that. I'm wondering if we don't even... Oh, no. So you'll see... you know what? Let me try just leaving that block as empty and give it a label. Accumulate loop. Let me compile this. That was a mistake. Return expected I32. We got nothing. Ah, yes. So I'm just setting up, before we write the loop, I'm just making sure that we have everything set up. So these are our variables. Then we initialize our sum. We have the loop, and then we have the return. We want to return the sum. Okay, so that works. And if we were to do this now, we should get a 0 because the sum is 0. So now block accumulate loop, what we're going to do is we're going to say local.get n. So we're going to use n as our counter. And it starts at the top, and we are going to go down. Because when we're adding, so we looked at this actually in memory.c, but when you're just adding, it doesn't really matter what order you go in. So we're going to start at the top and just go downwards since we already have the variable allocated, instead of setting another variable and comparing it. Instead of initializing a counter, say I, and comparing it to the integer every time, we can just use one less value. So we have our counter, and we will log this log num like so. So we need to get our element. So local.get address, because we need to load the element in from memory. So we have local.get address, and then i32.load. So we now have it in the stack. So, sorry, our stack has the address. Now, stack has the elements. Instead, it popped the address, loaded the variable, the data in from address, and now element is there. Then we have local.get sum, so we get the current sum. So S now contains element and a sum, and then we just want to add. So i32.add, because we're just incrementally adding it. So S now contains sum prime, which is just the updated sum. And then we want to set the local variable again. So set it back at sum. S contains nothing, but sum, the variable, because again we're just manipulating the local variable here, where it's now contains the updated value. So we have the new element, and now we need to increment. We need to essentially do our increment step in the loop. Increment step. So we'll start by the address, because if we just keep going from the address, we need to update this value. If you've taken any sort of course on assembly or looked at assembly before, there are a lot of ways to address in memory, and it's super, super, super easy with ARM assembly. God, once you get the hang of it, it's very easy. But we're just going to procedurally decrement the address, because in assembly there are no concepts of a pointer. You just have numbers. We just have i32s and i64s and whatnot. So we have local.get, and we need to update this address somehow. And since this is just a parameter, we can update it and set it as a local variable using local.set. So we're going to increment address first. So local.get address. Then we're going to say i32.const for i32.add. Then local.set address. So let's look at the stack here. So we have the stack is just address. Then the stack is address and 4. Then it's address prime after the addition, so address plus 4. And then we have an empty stack, but the local variable is updated with the value. Then we're going to update the counter. And note how this is going to look a little different. So we're incrementing the address because we start with our local variable at this value, just to save time and instructions. I don't want to, again, since order does not matter with addition, I can have the cursor moving up and the counter moving down, just as long as the counter breaks us and breaks out a loop when expected. So we're going to decrement the counter. The counter is just going to tell us, okay, you have n number of elements left. Okay, wonderful. So long as that counter is greater than 0, I know that the array is going to contain more elements. Hence, I know these addresses are going to be valid. So I can continue to add to them until we are out of elements. So we'll say decrement counter here. And we'll start by getting the counter. So local.get n, again, it's just a local variable, so we don't need to do anything new. i32.const 1, i32.sub. So now our stack contains n and 1, and then sub, our stack contains n prime, which is n minus 1. So the first element will be the right-hand side. So the top of the stack is the right-hand side, and the second top of the stack is the left-hand side of the operation. You'll see that ordering is maintained throughout. Sorry, I was just getting some more water. You'll see that ordering is maintained throughout any function call of that sort. Okay. So that's our new counter, and then we want to store it. So local.set n empty stack. Then, once we have the counter, we need to determine what to do with it. And this is going to be where our conditions come in. So we're not going to be using if-else blocks, but those don't exist in raw assembly, so I'm not going to care about them. I'm just caring about block. This is a label. If you look at any type of assembly, you will have labels and branch statements, but no if-else. That doesn't. It does exist, but not too much. People will more rely on branches and conditional branches. So we're now going to loop or terminate. Loop or break, essentially. So we're going to get our counter, local.get n. And again, make sure you know what your stack contains. Because you could just assume, okay, well, I subtracted here, so I don't need to reset this value. So for example, if I did not say local.setN and just use this as the counter, or here, I'll talk about this in a second because it'll make more sense. So we have n prime now as, so the updated counter. And then I want to compare it to 0. So this is just, again, going back to memory.c, while n, this translates to while n is greater than 0. So then we say i32.const 0. So now we have s, n prime, and 0. And then we're going to compare them and set a condition flag in the processor or in our WebAssembly sandbox. So you can do this using i32.gt, so greater is g, and then than is t, underscore s for signed. You can also do, there's a bunch of them. So i32.ge is greater than or equal. You can do less than lt. You can do less than or equal. You can do eq for equal, eqz, which is, I forget, it's another one. But then you can also do underscore u for unsigned comparisons. So it's pretty much like assembly. These are just all different opcodes when they get encoded into computer instructions. So i32.gt underscore s. And then if this is true, so if this results to true, so we essentially just pop this onto the stack. I'm actually wondering right now. We have I'm forgetting if this, we'll do some testing, but I think this pops true onto the stack, and then we use true in this conditional branch. So br underscore if. So essentially, if the stack contains true, or the top of the stack is true, then I want to break to loop, and loop matches the label up here. Wait, no, not the function. This. So the block has the label loop, and I want to say break if true to the loop. Otherwise, we're going to fall through to the return. So let's take a look at this. Let's compile first and make sure it works. Oh my god, it does work. Cool. So quick note before we go and test. If I were to just think, all right, so I already have n on the stack. What's the purpose of setting the local variable? All right, so let's just say I did not set the local variable. So yes, this comparison would still be valid. And then when we looped again, n would not be updated. This local would not be updated. So we can try this right now. Let's actually make sure it works, and then I'll demonstrate. So we'll compile. Okay, flow. Oh, I didn't even give you guys a function call. So we need to start with else if name equals flow, and then exports.accumulate. So we need to actually set our values in memory. So here. All right, so we're going to say variable array is equal to new uint32 array, because we're just going to set integers, memory.buffer, and I'll just start at address 0. So we'll say array at 0 is equal to 20, array at 1 is equal to 15, array at 2 is equal to 30, array at 3 is equal to minus 15, or minus 17. I don't know what the result should be. Can actually, just so I'm aware of what we should be expecting, let's actually just print it. Console.log expect 20 plus 15 plus 30 minus 17. And then accumulate now will take in 0 and a length of 4, since there are 4 integers in our array that we set, at least. Everything else is just going to be zeros. Okay, but again, I kind of neglected this point a little bit, but or I didn't emphasize it enough. But exporting memory, we now go to exports.memory here, and we are writing into a buffer that represents the memory. So we're communicating with WebAssembly through shared memory. Do I think WebAssembly could replace container technologies? Do you mean like Docker or something like that? If you mean containers like Docker, no, because WebAssembly still needs to run in a browser sandbox or in a JavaScript environment. Containers like Docker run in the operating system. They run so low level. It's not even. They run very low level. This is still in a JavaScript environment. I do think it could boost it. I'm doing a little bit of work with something like WebAssembly in a Docker container, and it's involving edge computing and internet stuff. But no, you cannot replace container technologies if you're talking about Docker. But let's run this example. Reload flow. Expect 48. I get a 4 from somewhere. And then a flow 20. Okay, I think what happened was we have this initial value. And I believe I tried to cut a corner. Because I didn't like something. I don't like having to specify a loop block here. But does this work? Because what I believe just happened was we got through the block, we called log number, which worked, did all this stuff, added the first element, so 20, and then we tried to loop, but break if loop doesn't work with looping to a block. So let me try and set, because label equals @1. I don't know what this means. Block. Do I need to say label equals that? So I need to put label in a comment? Is that what this means? Oh, wait. I think so these are control flow levels, if I'm correct. Break if one. Sorry, let me try. I'm trying to dissect this a little bit. Break if. I don't know why there are 2 elements here, but let's compile this again. Undefined label variable loop. Okay, so the label did work, but I want to say break if 1. Maybe that works. Expect I32. Type mismatch. Expected I32. What got? Okay, so that doesn't work. Is that okay? Unexpected token. Okay. I will do what I know works right now. You can set a block, but then you need to have a nested level here inside the block called loop. And this contains we'll change this label here. So this loop, this contains the label here. So So everything inside here gets indented. So we have our block, which contains the loop, which contains all our code. And then we now go to break goes to increment, this new label. So let me compile. Good. Flow. And we get it. Okay. So you can see our counter decrementing 4, 3, 2, 1. And then as soon as it hits 0, we break. It can. Yes, WebAssembly can run as a sandboxed binary, but again, you're still limited by the sandbox. You're not running. It does work kind of like a container in a way, I suppose, but it will never match the container because the container, those are optimized to work directly with operating systems. I suppose I'm kind of looking into something along the lines of this with the operating system series that started a while ago. One video in it so far, where we're trying to create an operating system in WebAssembly. And I suppose this lends to your question because it's kind of being a sandbox container, and it's going to have some operating system functions, but I'm not sure at the moment. We'll see where it goes. All right, so this works. I want to see if I can get rid of this because I really don't like having two. This doesn't make sense to have two things here. What the hell? Okay, but this works. Point is, this works. Let's do another quick function called average. So function average export average, which takes in param i32 and i32, and this will just average out. This will just average our elements. So averaging, you probably know, you just take the sum of the whole array and then just divide by the number of elements, and we have a function to now take the sum of the array, accumulate. So what we can do is just say local.get i32, sorry, not i32, 0, local.get 1, call accumulate. So stack is going to be the address. Stack is the address in n, which is required for our accumulate function. Then our stack is the sum. And then we want to divide by the number. So local.get 1 again. S is sum and n. And then we just say i32.divide. Divide signed. So the sum is, or the stack, sorry, is sum divided by n. And that's on the top of the stack for average. If we do that, expected this. I did not specify return type. Results i32. Perfect. And then in our JavaScript file, I want to say results as sum, and then I want to get the average. Which just takes the same parameters because it's the same array that we want to look at. And we are expecting and then I'm just going to do this as average. So I'm just taking the sum, and then in Java, this is in JavaScript again. I'm just taking the sum and we're getting the average of the array. So let's reload. All right, so expect 12 as average and flow 12. So we use our local variables here, call the function again, and we give it our use the local function to accumulate and then divide by n to get the average. Okay. I think we're at a good stopping point for the moment. I'm going to try and work on this loop increment here, but when we get back, I'm going to have this sorted out, and maybe we'll look at some if statements if we want, but I'm going to get branching down and we'll do a deep dive into some branching cases, but this is just some basic flow control. Anyways, hope you guys enjoyed. Stay tuned for some point when we'll be continuing this, and I want to use this in the operating system hopefully, which will be pretty cool. We'll look forward to that. Alrighty, have a good night everyone. Stay warm. It's pretty cold right now, but stay healthy and stay warm. Happy end of holidays. I don't even know what holidays come out next, but either way, enjoy yourselves. Have a good night.